This lecture is on ultrasonics, which is another technique of NDT, which is predominantly used in condition based maintenance as a non-destructive test technique to evaluate the effectiveness of, for example, welding, detection of cracks and so on. So, we will look into the principles behind this ultrasonics in this class, few applications and recent development in ultrasonics, that is the phased array technology, which is used in getting an overall idea while doing an ultrasonic scanning on an equipment. Okay. So, essentially ultrasonic waves are sound waves, and these waves are, as you define ultrasonics, any wave above 20 kilohertz, though in the case of ultrasonic which are used in fault detection, we use signals higher to frequencies of 1 megahertz and so on. These waves are very directional, and then they can propagate in a media and so on, and we will see how the propagation in a medium is affected if there is a defect, and then how we can identify those defects. Ultrasonic wave, another important principle of ultrasonic wave is the speed of the wave is dependent on the material property. Okay. So, for example, in steel, the speed of sound is about 5000 meters per second. So, one needs to know the different speeds of ultrasonic sound waves in a material, and then this wave, once it is incident, we will look into the, suppose this is an ultrasonic wave front going in this direction, and there is a certain depth to which it can go. That depends on the power of the ultrasonic wave, that depends on the frequency of the wave, the diameter of the wave and so on. So, that is what is used in the transducer design. So, essentially in ultrasonic we send a wave, and depending on the impedance, another important concept which I am going to introduce in acoustics is what is known as the impedance. So, Z is the okay. For example, I have a medium of certain impedance Z 2, which is P 2 by V 2, and the impedance of this medium is Z 1, which is P 1 by V 1, where P is the acoustic or sound pressure, V is the velocity. Okay. So, depending on the relationship between Z 1 and Z 2, some will be incident, some will be transmitted, some will be reflected and so on. Okay. So, the impedance of the material, if Z 1 equal to Z 2, the wave would get transmitted without no reflections. So, this is the physical principle of the physics behind such sound waves. So, depending on the intensity of Z 2, the reflected wave intensity and the incident wave intensity, we can find out some clue as to what is this Z 2 of the material. Now, if there is a difference in the impedance, this reflection coefficient, which is IR by II, will be dependent. Okay, they will vary, which is nothing but a function of Z 1, Z 2, and from a acoustics, you can find out what is the relation between reflection coefficient, between the transmission coefficient and so on. Now, if there is a defect in the material, say in the form of a crack or a void, defect in the form of crack or void in a material, this wave front is going to get reflected, sorry, Z1, Z2 and some new Z star. Now, if I move this is a probe. If I move this probe along the surface of the body and then this incident wave is set, there will be instances when the intensity of the reflected wave will be different than the intensity at this location. Say for example, I r star, at another location it will be maybe I r. So, by knowing the difference of this intensity, we can get some clue as to what is wrong in the material and so on. So, this is how ultrasonic waves are used to find out the presence of a defect, which in effect is because of a change in impedance. Another we make of ultrasonic wave is, if you look at this way, this is a material and we send an ultrasonic wave. So, this is Z2, this is Z1. Because it strikes impedance, discontinuous boundary, there will be reflections and this can be a transreceiver. So, if I move this probe all throughout, I can do couple of things. First is, with time I can see some ultrasonic wave intensity. Okay. So, this time period is nothing but responsible for, if this is L, the thickness of the material. So, the time period will be C by 2 L will be this time. Okay. T. So, indirectly, if I know the time period between such intervals where I send the wave and get the reflected wave, and if the speed of sound is known, I can find out L as 2 by 2 C, and this is the principle behind what is known as ultrasonic thickness gauge. This has lot of industrial applications. For example, in a pipeline has certain wall thickness, this is the pipeline, and this is to have a certain thickness, say T is its thickness. Now, this could be carrying some fluids in a plant, could be some fluid which could be corrosive, or otherwise there could be scale formation because of impurities. So, what would happen over the time? Either material would get deposited or material would get depleted because of corrosion. So, from the outside, if I put such ultrasonic probes, which I am writing as u t, so and then try to measure the new thickness t star or t dash. So, these thicknesses will be, in one case t star is greater than t, in another case t prime is less than t, where t is my original thickness. Okay. So, this kind of probes are used for measuring the thicknesses of pipes in chemical plant, process plant. Over the years, you would not know from the outside whether the pipe is having certain deposits in the forms of scale, or pipe has got corroded to a certain thickness. So, if you do a regular scanning by an ultrasonic probe along the length of the pipe, you can see whether the thickness variations are there. This is one application. Another application is, many times we have been to plants wherein I know a case of a paper mill wherein the owners of the paper mill actually bought a paper mill, the whole plant, out of the Eastern Europe from Romania, shipped them to India and installed it in a location in India, and they started producing papers. The plant was in place, but they were never sure as to what is the dimensions, because they never had any drawings of the sections, of the critical sections of that plant machinery. For example, in a paper mill, maybe in some of my earlier classes I had shown you the figures of those paper mills. There are a lot of rolls, and actually these rolls are held on frames, frames, this sort of thing, cross section, and these are bolted to the foundations. I am just drawing one of the front views, but nobody knows, there are a series of such frames put in the plant where this is the paper mill roll, and this is the frame, which is of course put on a foundation on the soft floor. So, in such a plant, there were cases where the thickness of this, though they knew this was steel, but nobody knew what was the thickness of this material. So, in such a scenario, we used to put ultrasonic probes, and then we are able to measure the thickness, and then we could reconstruct the entire plant machinery drawings in terms of, once we knew their thickness, we could measure the dimensions. So, what I mean to say is, a lot of unknown thicknesses can be measured using ultrasonic probes, because you have access from the outside, and then you can know the thicknesses on the appropriate places. This is one area where ultrasonic is used. Now, this wave, I have not told you about the type of wave. What is the type of wave? As you know, these are all sound waves, and sound waves in structures can propagate as shear wave or surface wave, and sometimes as longitudinal wave. And speed of propagation of these waves are different. If you look into any book on acoustics, they will give you the equations of these waves, which are propagating in solids, fluids, and depending on the type of wave, the speed of sound in these materials are different. And we will show you one general case. For example, this is a view wherein this is a body. So, if I have a normal beam probe, and this actually is perpendicular to the structure, this A is actually a longitudinal wave. Now, if I move it along this probe at an angle, this angle could be 45 degrees, 60 degrees, 70 degree, this is going to produce a shear wave, and this shear wave is going to get reflected out of this area, because this discontinuity, and then we can see if there was a defect in the path, there will be reflection at a different angle. So, this kind of waves can be produced by having an angle beam, otherwise, or we can reduce the angle like a total internal reflection, and then this will be almost on this surface. So, we can generate surface waves. So, and these are generated by these ultrasonic probes. Okay. So, what is this ultrasonic probes? What generates ultrasonic waves? How do we physically generate these waves? Essentially, what happens, there are in a transducer we have certain piezoelectric material and if a small piece of piezoelectric material is held in a casing with the right amount of stiffness, okay, this has a natural frequency Fn. This could be equal to maybe 1 megahertz or so, very stiff and thin, short, less mass element. So, we will have a very high natural frequency. So, if I excite this piezoelectric crystal by an oscillator, where I can generate a forcing frequency equal to 1 megahertz, this is going to resonate and then I will be able to generate ultrasonic waves. So, this is a very simple principle of having a piezoelectric crystal, P crystal, which could be made to resonate by a frequency which is equal to its resonant frequency, and then we can generate such ultrasonic waves. And these waves, if they are normal, they will be longitudinal, they could be at an incline, they will be shear. If I make it more inclined, and finally, I can get a surface wave. So, the same probe, depending on its geometry, can be used to produce any of these three types of waves. So, once such waves have been generated by an ultrasonic transmitter, okay, we can now have this wave propagating in a material, and then depending on the impedance of the material, because of a defect, discontinuity, void, crack, we can get a reflected wave, and depending on the intensity of the reflected wave in comparison with the intensity of the incident wave, we can get as to some clue as to what is the change in the impedance and where is the defect, and so on. So, ultrasonic application, if I was to just briefly write down what are the applications of ultrasonic waves, particularly in CBM. One, of course, was the thickness measurement, and the other is what is known as the void or crack detection. They are, of course, all NDT techniques, and this void and crack detection has a lot of engineering applications. Another one specifically for ultrasonic is weld defect identification. In some critical applications where welding is done, there are many codes like the ASME codes, ASME weld codes, which mandate that all welding have to be checked by ultrasonics. Okay. So, these are a lot of engineering applications. Another applications I will tell you, which coming out of Kharagpur, we have a big relay workshop here, and I must tell you. So, if you look at the railway wheel set, okay, this is the axle, flange and the tread. Okay. Imagine in a railway axle, if there was a crack which was internal, which has developed, maybe some initiation was there because of a weak material or something, and over the time this crack has become alarmingly big. Time will come, this crack is so severe that there will be a failure of the axle. Now, so you can imagine the disastrous consequence of an axial railway axle failure. Okay. So, how can you detect such internal cracks? Obviously, it is not visible from the outside. So, what they do in the railway workshop is they have an UT probe, and if you go to the workshop, you will see these guys will be scanning the entire surface of the axles over a certain period, and they have a periodic inspections of the axles. Okay, we'll come back to example of the welding pretty soon. So, the principle of ultrasonic transduction, which I just mentioned to you, that we have usually a piezoelectric crystal which is made to resonate at its natural frequency. So, this ultrasonic wave is generated, and the shape of the ultrasonic transducer enables whether the signal is longitudinal or it is in a shear mode or it is in the surface wave. And then we also have a receiver, and another technique is we can generate series of ultrasonic waves, and then it in one go I can have many ultrasonic waves going in as a array, and that they will get reflected back. So, this helps us quickly find out the defect. So, this is one of the latest techniques which they have been using in ultrasonics, and we have one such in our lab, and which you can see in our website www.iitnoise.com. So, all these instrumentations are available, particularly the ultrasonic phased array. Phased array probe. I will come to that discussion at the end. So, if I was to explain to you how this ultrasonic wave interacts, essentially this is the piezoelectric crystal. This is a material. This is a material which is being inspected. This is an ultrasonic crystal, and then this is the incident beam at an angle. This beam will get refracted, some part of it will get reflected, and usually we have a sound absorbing material here, absorbing material. So, that because we do not want any information from here, rather we are interested to where this beam gets reflected. Okay, and then looking at this reflected beam, we can find out the intensity of where this defect is, and so on. So, fault detection by ultrasonic probes, one is this internal crack and voids in any type of material, both metal and non-metal, and then is the thickness detection. Another very big advantage of ultrasonics is it can be used both in metals and non-metals. Many of you may be familiar, the doctors use ultrasounds for finding out the ultrasound sonography to find out if something is wrong with you, some ailment is there. Okay. And these are essentially non-elements. Only thing is that we have to know the speed of sound in that medium. Unlike some other NDT techniques where they have to be metal, like the eddy current testing or magnetic particle detection, method, okay, they have to be metals, but ultrasonic is it can be used in non-metals. So, this is where it is advantageous, though in many engineering structures we have what we know as the usually made out of steel. Now, I will give you another example how is ultrasonic used for weld flaw detection. So, for example, if I have two plates which are butt welded, so there will be some sort of a chamfer angle and these two plates are put together. So, there will be a weld deposit. I am showing this weld deposit, weldment or weld deposit, and this is plate A, this is plate B. So, what happens is, if you can think of it, this is a long plate and then there will be this kind of weldment. Okay. So, to see if this weldment is effective or not, what you can do is I can put a shear wave probe, I can put a shear wave UT shear wave UT probe. So, what it essentially does, it sends a beam and then it gets reflected, okay, and this gets into the weldment, and I can be traversing this weld probe one by one, okay, along the length of this weldment, and whenever there is a flaw in the weldment, if there is a flaw here, the intensity of the reflected wave is going to change. Okay. So, if I get an image of all the intensities of the ultrasonic wave along this line very next to the weldment, I can see a high intensity which corresponds to this kind of a defect here. Okay. So, that is how every weldment is checked against any internal weld defect. This is not possible by any other technique. These internal defects are not visible to the open naked eye. So, only thing is that nowadays there are many systems wherein this probe is traversing. This traversing is automated. Okay. And then there are softwares, and through good GUI software where the traversing is controlled, one can get an image of this length. Okay. And depending on as many such weldments are there, we can have the picture of the weldment. Another very important aspect while doing such ultrasonic probe is how do we ensure that the ultrasonic wave which we have generated is actually going and then getting reflected and not getting reflected from this surface, no reflection. So, to ensure that happens, usually a couplant is put, and this is nothing but a water based gel, so that good high signal to noise ratio of the ultrasonic wave is generated, and so all the energy ultrasonic wave gets transmitted to the medium. Okay. So, this has to be one important thing, and this surface in for example, in this case of no special treatment of this surface is required. Apart from that, a layer of couplant is to be put, maybe a layer of couplant is to be put. Okay. Now, depending on the nature of this traverse or the image, there are certain scan modes in ultrasonic. Okay. We will come to the scan modes pretty soon. So, this is another example wherein a thickness ultrasonic thickness probe is being used in the laboratory to measure the thickness of a material. This is actually a steel block, and if you will see here, this is about, we have put the centimeter scale here is about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, about 100 centimeters. Okay, and this is about 32 within eye approximation, and this is maybe bearing 2 mm of the gap here, which has been artificially created to explain to you or demonstrate to you how this ultrasonic UT probe, the red one is the transmitter and the other one is the receiver built into this probe. So, this has been calibrated, this is an ultrasonic thickness gauge, this has been calibrated to measure the thickness of steel. By in this thickness gauge, we have entered the speed of sound of ultrasonic wave in steel as 5000 meters per second, and this is measured as 68 millimeter. Okay. So, this can be used to measure the thickness, and this is the principle behind this ultrasonic thickness gauge. Another one was, this one was a metal surface. We would like to measure its thickness from the outside. So, 1.7. If this is not possible to measure by a ruler or by a scale, because you do not have access to the other side of the material, and you can see this fluid like gel like thing, that is the couplant which has been put between the material and the ultrasonic probe to measure the thickness. Okay. So, coming to the scan modes, there are 3 scans A, B, C. So, A is a scan wherein at a single point I do a measurement. B is actually a surface scan, or I would say a linear scan, quite not 2 dimensional. So, if I on the weldment I can do a B scan, but then a series, suppose this is a top view of a material. Okay. So, this is an A scan at any point, this could be a B scan, okay, and series of such B scans will actually represent as a C scan. Okay. So, these kind of scan images, A scan, B scan, C scan. So, C scan gives us a contour of where the defect is, and depend if there is a defect at a particular location, this should come up as a change in the color intensity. So, there are a lot of nice computer graphics in the softwares which drive these ultrasonic systems, where you can get a colored image, of the entire surface. Okay. But you will notice that in such a scenario, one has to anyway physically capture all the data at every A scan points and then put them together through a graphics. So, this becomes a little cumbersome and little tiring. To perform individual scans at every point. Okay, though as I was telling you, particularly for weldings in pressure vessels, nuclear plants, aircrafts, bridges. Okay. Some of the codes mandate that an ultrasonic scanning is done, ultrasonic test is done to find out the weld effects. Okay. And this is the principle people use to do find out the defects in welding, because the whole problem with welding, because if you would have seen in we will be studying a case study in many of the scenarios, because welding brings about high temperature in the material. This changes the metallurgical properties of the material in terms of its grain size, etc. So, particularly in welding, they do what is known as post heat weld treatment. Post heat weld treatment. So, because if you weld, you go up to the melting point of the material and maybe around 14 degree, and then if you cool with time the temperature, the rate of cooling has lot of influence in the grain size which is developed in the material. So, sometimes the materials can become brittle, sometimes they can crack, sometimes they become so brittle that they cannot sustain large fatigue loadings and they would fail. So, what happens usually after a post heat weld treatment, to ensure that there are no voids, no cracks, no defects, it is mandatory in such critical applications in pressure vessels, nuclear plants, bridges, etc. They do 100% ultrasonic testing. Okay. It is only because of this, and that is the reason in many cases, particularly in aircrafts, etc., you will see wherever possible people try to avoid the welding and then maybe go for riveting, because with welding the most worrisome thing is that I could be changing the metallurgical composition of materials, and when you will see in condition based maintenance, many times failures have occurred not because the plant was not running within the limits, everything was safe in terms of the rotational speeds, operational speeds and loads, but because of an inherent material defect right in the manufacturing stage of the plant. Maybe a conveyor system, the brackets in a conveyor system or the towers or the rails, they broke. There have been cases where the conveyor, the pulleys in a conveyor drive system just sheared off, because the way the pulleys are made. I will just show you one configuration of one drive pulley. For example, if you look at the pulley, it is basically made out of two discs, okay, which is put at two ends, and then there is a roll, cylindrical roll, and there is a shaft which is shrunk fit. Either sometimes it is right here or sometimes it is through and through also. And then there are bearings. Sorry. Okay. So, many a times these areas welding is done. This is one area where welding is done. Okay. There has been cases where we have seen that these materials fail in this crack, occur in such pulleys, they are known as drum pulleys. Okay. And this couple of reasons, because no proper post weld heat recovery treatment was done, and so this kind of failures are not because of the operating conditions. Operating conditions are good enough. Okay, but because of no proper heat treatment, and such cases they recommend that an UT inspection is done. I'll report to you a case study where we did do the metallurgical analysis of this failed structure, and we could find out that there is a difference in the microstructure because of such harsh heat generated during welding. Okay. Now, we will come to another technique, because by now you must have realized that by ultrasonic I can have a probe, generate a wave, see its reflected intensity. By some way measuring the reflected intensity, we get couple of things. One is the flight time duration, which can be used to measure the thickness, and if this thickness is because of a scale formation or because of a corrosion, we can find out the change in thickness. Next is this ultrasonic probes can be used to find out internal defects like a void or a crack in a structure. But you must have realized, if there is a big structure and at every point if we have to do an ultrasonic scanning point by point, this becomes a humongous task. So, recently what has happened is basically a phased array probe is been made. It is basically a long phased array probe, which is cut into many different piezoelectric elements like this, and phased arrays are in which the timing of the element's excitation can be individually controlled to produce desirous effects such as steering the beam axis or focusing the beam. So, through an electronic timing of these phased arrays, these piezoelectric crystals, they are equally spaced though. So, I can excite them in one go. So, all of them will generate ultrasonic waves, or I can excite this earlier than this. So, then the flight time will be different, and then I can steer them or I can converge them. So, all these operations are possible through an electronic controlling mechanism. Or a circuit. Okay. Now, such structure, I mean this could be held together, maybe there are 16 elements, usually probes are found in 16 elements or 64 elements. So, imagine instead of one probe, you have 16 probes or 64 probes in one go. Okay. So, for a quickly they can help you do the scanning. So, this is what is the phased array beam forming which happens. So, we have an acquisition unit, okay, and then they will send the pulse, and then we can get the there is a flaw, and then this internal the echoes will come because of the reflection, okay, and then depending on the phase delay or depending on the intensity, we can find out the defect, location of the defect. So, but this require very precise pulsing and very precise estimations of calculating the time delay. Imagine you are talking about waves at 1 megahertz or 2 megahertz. Okay. So, this require very fast because the time delay, as frequency, time delay is inversely proportional to frequency. The higher the frequency, time delays will be less, and we have to be very careful or have very fast processors to capture such signals. Okay. So, this is where is being used currently, and this equipment we have in our lab. Okay, and use this, and this is just to show you how focusing can be done. Elements are pulsed, these are the elements with different time delays. Okay. And these elements, if more delay is applied, less delay is applied. So, depending on that, they will focus onto a surface. Okay. So, these are all gimmickry of the electronic circuit, which helps you generate a wave. So, I can focus it, if I can steer it. So, all these scenarios are possible through such phased array processors. There is another example for shear waves, because shearing I have to slant it. So, I have to steer it. So, I can generate a increasing time delay, and then I can generate a shear wave. Okay. So, this angle can be changed by the delay, and that is the beauty of such phased array probes. Okay. So, this ultrasonic probes are available in many forms. One is the longitudinal probe, other is the shear wave probe. Shear wave probes are actually angular, and then we have the phased array. Phased array probe is actually many such ultrasonic probes held together, and through electronic circuit we can generate. Okay. And sometimes the transmitter and the receiver are held together in one unit. So, beams could be again used to focus. They will all converge and finally focus. So, in these are the phased arrays, the green ones are the phased arrays, but you can see by changing the control circuit, many configurations are possible. Beam steering, straight, inclined, asymmetrical, and so on can be done, and then this will help you to find out the flaws. Another is this linear scanning. Okay. This is what I was talking about. There are certain active groups, the 64 element probes, then you can scan them, and then the scanning method could be like this. You can probe them. So, the entire surface can be scanned, and you can get the intensity of these waves. Wherever there is a defect, intensity is going to change. So, you can get an image, a C scan of the ultrasonic test, and this is how it can be done. Okay. And all you have to do is hold the probe and just traverse it, and there are 16 active elements, okay, into the probe, and lot has to be done with the cable, because sometimes these cables in these probes are also equally costlier. Okay. So, this is a probe, and then we have a cable and the signal processing unit. Of course, this interface with a good GUI based software. Sometimes care has to be taken, because they are all piezoelectric material. these cables, you typically in a plant, this has come in standard length from 5 to 20 meters. Okay, so you could be traversing the probe depending on whichever scan mode, and usually C scan can be done with such phased array probe. Okay, and then you can get a GUI software where you can get an image of the system. So, this is one method by which the linear scanning is done. You can see the graphics, okay, one by one. So, this is just by moving the electronic signal stimulus. Physically, the probe has not moved, probe has stayed on the entire surface, but just by moving the electronic energizing particular element, my waves are being generated. So, you can scan them accordingly. So, this is what is known as the electronic scanning or linear scanning. It is the ability to move the acoustic beam along the axis of the array without any mechanical movement. Okay. The beam movement is performed by time multiplexing of the active elements. Scanning extent limited by number of elements in the array, number of channels in the acquisition system, because this is a multi-channel acquisition system. So, this as I was telling you, instrumentation has come a long way to help the ultrasonic particularly condition based maintenance, and recently earlier we used to have just single element ultrasonic probes having resonance piezoelectric crystals having resonating structures, but nowadays through such electronic linear scanning we can produce beams and we can do the scanning almost immediately. So, these are some of the views of the different phased array scans. Excuse me. So, these are the different this is a sectorial scan, this is a linear scan. I am sorry. Okay, and then we have a linear scan, and then this is a combination of the scan, how they are arranged in the probe, different elements, and then this can be scanning. So, all along the wedges, this suppose is an weldment, you can do the scanning and find out. So, the advantage of phased array ultrasound scanning is high speed electronic scanning without moving parts, improved inspection capabilities through software control of beam characteristics, inspection with multiple angles with single electronically controlled probe, and greater flexibility for inspection of complex geometries and so on. Okay. This is one such phased array system which we have in our laboratory, wherein you can get an image of the area where you are scanning, and this is very similar to the doctor's ultrasound sonogram which you would have seen. So, we can see a defect according to here in the C scan. Okay. So, ultrasound has become very popular because of this softwares which are available and because of the advantage in phased array electronic systems which can be used for doing a quick scanning of systems and finding out defects. Thank you.